All right. So, good morning. All right. So, I think I managed to post some assignments. We'll see how I did. I'll show you where they are. And if they're not working, let me know because I don't know if I did it right. Okay, so they should be here. I just put them at the top of our page because why not? And I just grouped them all together. So I did post 4 assignments. They're not very long, so don't worry. But I will take a screenshot here. And I think I'll have to update the due dates because I think it's a little short on time here because I'm pretty sure I put them all to the 12th. But how about this? I'll move them all to the 15th, so next Friday. So I'll put that in here. Assignments 1, I'll do 2, 3, 4. I'll have to change it, but they should be due even further. I can't do more. They're not very bad. Okay, so don't worry. Okay, due Friday, October 15th. Just 27 questions for one of those. They're not bad. I'll even show you. So they go in order of the stuff that we've covered. Oh yeah, the iPad doesn't like, okay, never mind. I can't show you, but you can have a look. It'll save your progress and stuff like that. So yeah, don't worry. I know. Just try it. And if they're way too long, then you can tell me. But for now, I think a little over a week to do them is good. Okay, so those are the assignments. It will be fun. That's right. I promise. I can guarantee it. You'll have fun. Okay, so what else? Oh, and remember I put this formula sheet here. That might be nice just as we move forward, especially for probability, just to have some place with all your formulas. Notice that there's an assignment 1 for probability and then an assignment 2 with a little bit harder probability questions. Okay. And we'll introduce one set of tables today. All right. So as a quick review, and I mean pretty quick, we started talking about the normal distribution. The normal distribution is kind of the most common distribution that we have to deal with or see even. And we know that we're always pushing for a normal distribution because it opens up a bunch of analyses for us. So we need to kind of be comfortable with the normal distribution. So we start with, well, it looks like this, right? It's centered on the mean. Okay. And what I'm going to do is I'm just going to do a little dotted line there. Oh, it's all curved, but I think you get the idea. Okay. And so here on the x-axis, let's call it, here you have your observations. then what we said was that the area under the curve, this area here, that's going to be a probability. What does it mean? It means that observations that are hanging out around the mean are more likely to happen, right? Because the area under the curve is the largest around the mean, right? And so we can use that. And as we move out further out into the tails, notice that the area underneath the curve gets smaller and smaller and smaller. It never actually closes on the axes, right? But essentially the area gets so small, right? That we call it approximately zero. Okay. What else did we say? We said, well, as a rule, for any normal distribution, I can fit 3 standard deviations underneath the curve before I have just a small area left, right? And so if I go here, 1, 2, 3 standard deviations, same thing above, 1, 2, 3 standard deviations. So I can fit 3 standard deviations on either side. And then the area in the tails gets so small that we don't need to go any further. So here I go 3 sigma and 3 sigma. If you're in business, which maybe not really, I don't think, but there's a program called 6 sigma, and I'm pretty sure it has to do with this, right? 3 + 3 is 6, and it's like an efficiency thing, but I don't know anything more about it, but kind of fun. So what did we say? We have, as a rule, right, we've got the 68, 95, 99.7 rule. So we can use that to approximate areas under the curve. Today, we're going to introduce, well, how can we get more precise areas under the curve, right? But we can use the 68, 95, 99.7, and I'll follow it up with a percentage here. Yeah, so the tail is the risky part of everything. So 68, 95, 99.7 rule to approximate areas under the curve. Okay, today we're going to develop a little bit more precise ways of finding areas under the curve. Okay, so here, today, we will develop more precise methods for finding areas under the curve. Why do we care about areas under the curve? Because they're probabilities, right? What's the probability of this extreme thing happening, right? And so today we will develop more precise methods for finding areas under the curve. I should say normal curve, but here, what I'm really saying here is probabilities. Okay, so that's important, right? To remember that the area under the curve, that's a probability, okay? So we need to develop some knowledge before we can get there, but we're gonna get there. Okay, so let's see here. Our goal, and maybe I'll do here. Where do I stop? Maybe there. Our goal is going to be to see if something is going to be extreme or not. So in statistics, we're always concerned with these extreme values, which means, are they out in the tails, right? We're always concerned with the tail, and we've seen that before, right? When we talked about skewed distributions, we said, oh, it's always skewed in the direction of the tail because those are the values that I'm concerned about or interested in, right? It's the ones that are kind of run of the mill, those I don't care about so much. Okay. So our goal is going to be to figure out if a value is extreme or not. So as a general rule, hey, I don't know what that is. It's just a right square bracket with a teardrop. It's a sad square bracket. Okay. So here, as a general rule, we're going to say that any value that's within the central 95% of the data, we're not going to be concerned about that. Those are allowed to happen, and we expect variability because we're talking about a variable, right? So we're expecting things, to measurements or whatever, to be, different to some degree. And so we allow for data within the central 95% to just happen, right? We're not concerned about those. Anything beyond that 95%, and if we go back to our empirical rule here, from mu, if I go to mu minus 2 sigma and mu plus 2 sigma, that's when I have 0.95 here, right? So really what we're saying, yes, but you're getting way ahead of us here. So we'll just take a step back here. Okay, so we've got the central 95%. Yeah, and don't worry, we will get there if you're reading the chat. So okay, so we've got the central 95%. That's what we allow most of the time. And so what we're going to say is that if a value is more than 2 standard deviations away from the mean, right, either above or below, right, below or above, then we consider it an extreme observation. Okay. What does that mean? Well, it means that we need to be able to figure out how many standard deviations a value is from the mean, right? And we're going to have a calculation that helps us do that, but we could also just do it, right? You can develop the formula and you can have the formula, but I just want to show you that the formula is just exactly what you would have done if you had to do it in your head, right? And so if you think about something simple, like if the mean is 6 and the standard deviation is 2, how many standard deviations is an observation of 4 from the mean? So what I like to do when I just map this out is I just draw a number line. It keeps going and going and going. Okay. And at some point I have mu equals 6. The point that I'm interested in is at 4. So what I'm going to say is I'm going to say x equals 4. X is always going to be the point that I'm interested in. Okay. So x will always be the point I am interested in. Okay. So now if sigma is 2, right, how many chunks of 2 can I fit in here? Well, you would probably say, well, this distance here is 2. So a distance of 1 sigma, right? Or 1 standard deviation. What are you doing here? All right. Well, you're taking this distance between the mean and the observation, right? And then you're dividing it by whatever your sigma is worth. Okay. And so what we can do is we can develop a formula But first, I just want to show you why. Where do I go to? Yeah, let's just do all of it. So slow. There. Oh. There. Okay. So because we know the distance between 4 and 6 is 2, we can fit one standard deviation in that distance, right? Which means that 4, so the observation of 4 is one standard deviation below the mean. Now, if we reconsider another observation like negative 4.91, okay, now all of a sudden gets a little bit trickier to kind of wrap our heads around it because we don't have that obvious cutoff of, intervals of 2, okay? But we can use the same approach that we had down here. So now, let's see here. If I go kind of down below here, if I start and I have mu equals 6, and I'm interested in an x equal to negative 4.91, I would still find this distance, remembering that it gets a little bit tricky because we're crossing 0 at some point, right? So you want to be careful, but how do you capture that? You can take 6 minus, no, you can't. Let's see here. This distance. This distance is going to be, yeah, you would do mu plus, but I want it to match the formula. So that's why I'm like, no, I said it wrong. So if I take x minus mu, right, then I would have negative 4.91 minus 6, right? I could do mu plus, but then I'm not capturing the fact that it's below, right? And so if I do this, then I get negative 10.91 probably. Who knows? Yeah. Okay. And so what's important here is that this negative is capturing that it's below the mean. Okay. So negative indicates, and I'll try to get up on a line here. Whoa. Negative indicates x is below the mean. Right? So you could have done 6 minus negative 4.91, but then you lose that, that negative, right? And so to retain that, that's why we do the x minus mu. Okay. And I like to show it on a number line like this, because eventually we're going to move towards, okay, what's the probability of having, so probability, remember, is an area under the curve. So what's the probability of having an observation of negative 4.91 or less, right? So then what we would do here is we would kind of put a, oh, this should be in the center, but I'll try again. Okay. So that number line is always going to be at the base of your normal distribution, okay? And so it's not going to be that weird. We're just putting a normal distribution on top, okay, eventually. Okay, so if we have a distance of 10.91, so negative 10.91, once I divide that by the standard deviation, then I find that the distance divided by sigma is going to be negative 10.91 divided by 2. which is, I'm going to steal it from here, negative 5.455. Wait, what happened there? Negative 5.455, which means what? 5.455 standard deviations below the mean. Yeah, definitely an outlier, right? So what we said was anything, so any observation that's more than 2 standard deviations away from the mean, either above or below, is considered an outlier or an extreme value, right? And so, so here, right, if we're 5.455 standard deviations below the mean, that's a very rare occurrence, right? And we knew that because we kind of had a good idea about, okay, if the standard deviation is 2, then from 6, I can go within reason, right? I could go from 6 to 4 to 2, I guess, to 0, right? And then anything beyond that is definitely going to be rare. Yeah, like a tornado in the Okanagan can happen, but unlikely, right? And so for that reason, that's the same reason that these axes go to negative infinity and positive infinity. So it keeps going and going and going because it's making room for, well, it can happen. It's just extremely unlikely, right? And so what can we do? Well, we have this, let's see here. So if we're interested in how many standard deviations an observation X is from the mean, we can find what we call the Z-score. So the Z-score tells us how many standard deviations away from the mean an observation X is, okay? So we're using that same notation of X is the observation that I'm interested in. Okay. So this formula, you would have gotten there if you had to just figure it out on your own. But from now on, you can just put it on autopilot and go for it, right? If you have to find how many standard deviations below the mean or above the mean something is, then you can just calculate the Z-score. Okay. So same thing. Wait. Just grab this whole chunk here because it's got that note about negative and positive Z-scores. But we already talked about that, but it doesn't hurt to bring it up again. In fact, I'll highlight it for you. Right, so what we can do is we can set up our formula. So our formula is Z equals X minus mu over sigma. And then our X is always going to be the observation that we're interested in. And then we subtract the mean just to retain that negative, and then divide by 2, which is our standard deviation, and then we get negative 5.455, which is exactly what we found, right? Because we're doing the same thing. Good. So let me see here. Got another example. So if mu is 6 again and sigma is 2, just keeping with those 2 values, how many standard deviations is an observation of 7.32 from the mean? So again, what I want you to do is draw it out, right? Because that helps you visualize it, not because you need it for this calculation here, but because I want you to build that that first step up of drawing the situation out because then later when we plop the normal distribution out on top, then it'll be a lot easier to kind of think about. Okay, so if you start with this easy situation where you're just drawing a number line to see how far things are from the mean, then it becomes a lot easier to draw the normal distribution to solve problems later on. So again, I'm going to put my mu equals 6 somewhere, and then my 7.32 is my x, so x equals 7.32. And so now what I'm going to find is, instead of doing that calculation where I find this distance and then divide it by 2, I'm going to set it up with just the z-score formula because I know that's what it's doing. So if I take z equals x minus mu over sigma, you should always write out your formula before you fill it in, right? That's for you when you look back at your work. What was I doing here? It's for me when I'm marking your work, right? To make sure that you kind of knew what you were doing, what formula to use, and it just makes it look a little bit nicer. Sometimes I'll slip up and I won't do it, but for the most part, try to do it. So then my x is 7.32 minus my mu is sigma, and my mu is 6, and my sigma is 2. Too early for me. Yeah, so then here, z is going to be, where's my calculator? I know you guys have done it. 7.32 minus 6 is 1.32 divided by 2, puts me at 0.66. I can read this as an observation of 7.32 is 0.66 standard deviations above the mean because it's positive, right? So here I can read this as an observation of 7.32 is 0.66 standard deviations above the mean. Okay. So that's how I want you to think about z-scores. So what's nice about z-scores is that they're standardized values, right? It doesn't matter what the mean is or what the standard deviation itself is. Once you've calculated a z-score, what's going to happen? Well, the mean is going to shrink down to 0, because if you think about 6, how far is 6 from 6? Well, it's 0 standard deviations away from the mean, right? Because it's itself. Then if I go to 4, right, that would put me at a z-score of -1, right? Because 4 minus 6 is -2 divided by 2 puts me at -1, right? So z-scores make this standardized distribution. And so z-scores are standardized values, and they're going to let us compare observations from 2 or more distributions. So even if they don't have the same mean and the same standard deviations, by standardizing values, right, then we're able to look at, okay, well, if you were 4 standard deviations above the mean and I was 3.2 standard deviations above the mean, then you were further from the mean than I was, right? It doesn't matter which group you're coming from. So a really common example is in the States, they write the SAT or the ACT. So 2 different tests, they're on 2 different scales, but they're meant to test the same thing. And so what you can do is you can standardize those values to compare students, right? And so that's usually the textbook example that they use. So I try not to use it, but sometimes it's tempting. Okay. So we're going to call the distribution of z-scores the z distribution. It's also called the standard normal distribution. So I'm going to bring in that little note here. put it down here. Okay. So sometimes we'll call it the standard normal distribution. Sometimes I'll call it just the Z distribution because I think that's more to the point. Okay, good. So just a couple of facts about the Z distribution. And how about the whole kit and caboodle here? Okay. Uh-oh, I ran out of room. So some facts about the Z distribution, right? If you're taking an observation from a normal distribution and you're standardizing it, then the shape is going to stay normal, right? And so here, if I have Z down here, then the shape is going to be a normal distribution, kind of like this. Okay. Like we said, the mean, if you have an observation that's equal to the mean, then that's going to be 0 standard deviations away from the mean, right? And so what's nice is the Z score or the Z distribution is always centered on 0. That gives us more properties, right? Because we know the normal distribution is symmetric about the mean. And so what does that tell us? So immediately we know that half of our curve is to the left of 0 and the other half is to the right of 0, making this the 50-50 split, right? The probability of being less than 0 is 0.5, and the probability of being greater than 0 is 0.5. So Z has a mean of 0 and Z has a standard deviation of 1. Okay, so what that means is we have here at -1, -2, -3, 1, 2, 3. So just as a rule, Z scores, they do keep going and going and going, and that's going to come up later. There's one problem in particular where you're going to find like a Z score of 12 or 13 or something weird. And then that's when I always get messages saying, I don't know, I think I did something wrong. No, you didn't. What you found was just a very rare occurrence, right? And so the probability of that happening, right, if you're way out in the tail here, the probability of that happening is very, very small, right? So what we use is we can summarize these facts using this notation, okay? And so how you read this is Z follows a, so this tilde is shorthand for follows a, okay? And I'll show that here. Z follows a normal distribution, which is referring to this n here with a mean of 0 and a standard deviation of, let's see here, and a standard deviation of 1. Okay. So that's the shorthand that we use, and so it summarizes things really succinctly, so we use it quite a bit, and we can use it in general too. So we can generalize to any normal distribution where X, so an observation X follows a normal distribution with a mean mu and a standard deviation of sigma, right? And so we can use this notation just to summarize the distribution. Okay. So what we can do is we could, let's just do it. I'm going to see if I can grab this whole thing. I was looking and I think this image, it's going from 4, it should be going from 3.4. I must have forgotten to update it. So just ignore that. We'll draw our own. We'll draw our own, thanks. I know I drew that one, but that was a long time ago. So let's bring this in here. So what we can do, right? This looks familiar, right? This Z distribution, I've managed to fit 1, 2, 3 standard deviations on either side of the mean. The standard deviations for Z scores happens to be 1. And so it makes this nice compact situation. So we can revise the 68, 95, 99.7 rule and say that the area between a Z of -1 and +1 makes up the central 68% of the curve, right? So the probability of being in there between -1 and 1 is 0.68, right? Same thing with 2. So -2 and +2, again, that's that central 95%. And then -3 and +3, that's the central 99.7% of the curve. Okay, so what if we have a situation like this one? So now, this is the first time that we're asking, okay, what's the probability? Okay, so I'll highlight that. What's the probability of an observation being less than 3.4 if the mean is 5.3 and the standard deviation is 1.2? Okay, let's just map it out on a number line, just like we did before, to see what it's going to look like. I am going to leave some room above my number line to draw that normal distribution. And usually I end up drawing the normal distribution first, but I just want to show you that you could do the number line first, just to make it a little bit easier. So I've got a mean of 5.3, which I'll put here. And the point that I'm interested in is at 3.4. And remember, we use X to denote that point that I'm interested in. So X is 3.4. And the standard deviation is 1.2, which I'm actually just going to jot down somewhere here. I'm not going to draw it on the number line or anything. This keeps going and this keeps going. So now what I'm going to do is I'm going to first attempt at drawing the normal distribution on top here, right? Because if I want the probability, right, that's actually asking the area under the curve. The area under the curve for what? Well, it depends on the question, right? Of an observation being less than 3.4. So the area that we're interested in is going to be from 3.4 and less than 3.4, right? You don't want to integrate this, I promise. So you really, really don't. People have done it for us, so we don't need to. Or we make R do it. That's not what we're here for. I know you guys just want to integrate stuff. And I'm like, it's a no for me. So anyways, okay, so if I want the probability, I want the area under the curve. So what I can do is I can, well, here's my first attempt. Okay, here we go. That wasn't very good. What's the problem? Well, I didn't put the hump over. So maybe I'll try it like this. Close enough. So the area that I want is going to be this area. So now, yeah. So this is the area that I want. Woo. Okay. Usually I show that with a little question mark. I like to have a question mark for where, just to remind myself what I'm solving for. So I do a little question mark like that. So the first thing we can do then is, just using the tools that we've developed, is, well, I could figure out how far 3.4 is from 5.3 with a standard deviation of 1.2. And what I'm going to find is that if I take that distance and I divide it by 1.2, I find that 3.4, and I'm noticing the little decimals hard to see there, 3.4 is 1.58333 standard deviations below the mean, right? Which we saw here. Okay. So what we can do, we could, if we wanted to, we could use the 68, 95, 99.7 rule. Okay. What would we do? We would probably shrink this down, right? We can kind of funnel this down into something kind of, I'm like trying to draw some sort of funnel. Here, I'll do like, all of this can be go down the drain. And what happens when we standardize it? Well, now, hey, that one's beautiful. Now that 5.3, that mu of 5.3 is going to be standardized to 0, right? So now all of a sudden it's centered on 0. Sigma is 1 all of a sudden, because I've standardized it. And this X, this 3.4, well, on a standard normal curve, it's at negative 5.83. So it's going to be down here, but it's the exact same situation, right? So here, this observation is at negative, oops, not negative 5. That would be bad. Negative 1.583. Whatever. So then the area that we want here is still that area. Right? I guess I should have, you know what? I shouldn't have put it so far into the tail. We draw these curves just to visualize things, but the reason that I'm hesitating now is because I want to show you where 1 standard deviation and then 2 standard deviations go. So I'm just going to bump that over just real quickly here. I'll put it here. Easy. Okay. So then the area that we're trying to figure out is this area here. So we could use the 68, 95, 99.7 rule, and it's a really good rule of thumb for just approximating probabilities. In fact, I've taught this course without any Z tables or anything like that, because we would typically just use software to find exact probabilities or more precise probabilities, I should say. So you could just use the 68, 95, 99.7 rule, but we're going to use a Z table. Okay, so that's what we're building up towards, because what you'll see is that if you have -1, well, -1 might be here. Then we know from the 68, 99, 95, 99.7 rule that the area below here is 0.16. And you can think about it, right? So -1 and +1, the central 68%. So then if I figure out how much is in the tails, it's 32%. And then I divide that by 2, I get 16% or 0.16, right? Whereas maybe down here at -2, the area, what's the area in the tail from -2? Well, again, so -2, +2, central 95%. I have 5% split between the tails. So now I have 0.025. You can see why that leaves us wanting more, right? Oh, I don't know, the probability is somewhere between 0.025 and 0.16. What's the big deal? Well, there's a huge difference between a probability of 0.025 and 0.16. Notice that because we've got the slope, we can't just take the average, right? Because the area under the curve doesn't increase or decrease that way, right? And so, so here, right, this is a really small probability. So the probability of Z being less than or equal to -5.8333 is somewhere between 0.025 and 0.16. I have introduced this probability notation, but if you just kind of take your time and just read it piece by piece, kind of makes sense, right? The probability is the area under the curve. And then the z-score that we found was negative 1.58333. And we want the area below that value, right? And then we find that it's captured somewhere between -1 and -2. Those are the only cutoffs that we have right now. But we're going to have more. Okay, so we could say that, and that is fine, but we want to be a little bit more precise. So let's see here. See if I can bring in this whole chunk, because they're just instructions that we'll read through. Oh, I might not have space. There's an issue. Crop top. Okay. Whoops. All right. Don't want to cut anything off here. I think I saved it all here. Okay. So like I said, this approximation works. That's fine if you are comfortable reporting that to your boss, but might be a little risky, right? So for more precise probabilities, we are going to use what's called a Z table. And so I posted those tables on Moodle, and I wonder if I have them brought in here or if I need to grab tables too. Nope. I'm sure I can search. I just don't know. There's the formula sheet. Okay. Bring it into us. How about that? Wow, that was long and unnecessary. Okay, so the tables, so you want to be a little bit more specific than that. And I'll show you right now. Okay, so the Z's table, sometimes we call it table A. This is the Z table that I like. Okay, there's a different Z table. It looks a little bit different. I think this one's cleaner. There's the table that I don't like is the one in the textbook, but I mean, you have it, so you could use it. They have the same probabilities. Now, the Z table looks like this. Okay, so it's going to have the first whole number, or the whole number, and then the first decimal is going to be in the left-hand margin. And then what we're going to do is we're going to have the second decimal in the top margin. Now, what this table is doing, and all it's doing, is it's giving you little cutoff points and saying, okay, at each cutoff point between -3.49 and +3.49, then here's the area to the left of each of these points. Okay, so let's go back there. So what you're going to do is you're going to calculate the Z-score, right? So if you want to find the area under the curve, and then we're going to round Z to 2 decimal places, okay? And this is to match the table. So that's not something you need to memorize. What you're going to find is you go to the table and then you think, oh, I can only handle 2 decimal places. So then you go back and you round it to 2 decimal places, right? And so you're going to have to round properly to 2 decimal places. What you're going to do is you're going to draw the normal curve with the area of interest shaded, right? It depends on the question that you're answering. So before we wanted the area below Z of, they look the same. All the Z tables are the same. The T tables differ quite a bit, but Z tables, they're always the same. unless you're in psychology, they have like a really weird Z table that they like to use. It's like the area between the mean and that point is this. And then, anyways, we're not using that. For some reason, they have this like very weird Z table, but they're giving the same information. So what you want to do is you want to draw this curve just to visualize things that are going on. That's going to help you later on, right? It won't make sense to draw the curve right now. That's okay. Just stick with it. So then go to the Z table and find the whole number and the first decimal of Z in the margin on the left. Okay. Notice that there's a negative page followed by a positive page. Right. And so you have to make sure that you've got a positive or a negative Z score, because remember, that's going to determine if you're above or below the mean, right? If the Z table, and I'm getting ahead of myself here because I should just read the instructions and then talk about it. So then what you're going to do, so you're going to find the whole number and your first decimal in the left-hand margin, and then you're going to use the top row, right, or the columns to find your second decimal place. And then you're going to join them up, okay? The table entry is everything in the body of the table. So the table entry that you land on is the area to the left of the Z that you gave it, okay? So if I just bring in, and it's got this little reminder here on the Z table. That would be nice if, especially if we were doing these things in class, right? Then for a test, you would only have the Z table in the formula sheet. Uh-oh, scary, right? Then you would have this little reminder here. Okay, so the table entry for Z is the area under the standard normal curve to the left of Z. Okay, and so if I just focus on this top bit, I'm going to copy this into our notes. Okay. And it's going to be so important that we understand how this Z table works. Okay. So what we could do is we can find, okay, what if I have negative 3.34? What if I have to draw that? Well, it means that if I have a normal, so a standard normal curve, that's Z, right? Z is centered on 0. And what I've said is, okay, if I have a Z of negative 3.34, what we're told here is that this area is 0.0004. It always goes to 4 decimal places here. And so you always want to keep all those decimal places, right? You don't want to mess around and lose any of those. Okay. And make sure that you keep all your decimal places, or sorry, all your zeros. Also decimal places, but all your zeros. So what you're going to find is that it's just going in intervals of hundredths, right? Second decimal place. And so all it's doing is it's giving the area to the left at negative 3.49, negative 3.48, negative 3.47, right? And so it's just cutting it down. Gets a little bit weird because negative 3.49 is the smallest possible Z. Why is that? It's because the area to the left of negative 3.49 is 0.0002. It's so small that anything beyond that, we don't really care. We can just say it's really, really small, right? Approximately 0. So here, right, the smallest area to the left is 0.0002. Okay. Z scores beyond that can happen, but they're very unlikely. So we don't really care how unlikely, because all we need to say is that it's less than 0.0002, approximately 0. If you flip to the other side of the Z table, what you'll find is that it maxes out at positive 3.49. Positive 3.49, what you'll find if you go to the positive side, and just so I'm not drawing all over the place here, I like to pull up arrows and then do them kind of above the curve, if that makes sense. And so if we go to 3.49, so positive 3.49, notice at 0, wow, let it catch up here. 0 happens twice on the table. That's just so you're not missing a value. There's a -0 and a 0. They're the same, right? There is no -0. But a Z score of 0.00 has an area to the left of 0.5, which means that in the Z table, all our areas that are for positive Zs are going to be greater than 0.5. That's a good check-in point, right? So if I go to a Z of positive 3.49, I find that the area to the left is 0.998. Maybe one more 9 in there. Let me draw it on here. 0.9998. There, I was missing a 9. What does that mean? Well, we also know that the total area has to be 1. Right, so that means that this area must be 0.0002. You can leverage that symmetry, right? And that's just going to come with practice and working with different Z scores and different areas under the curve. But this symmetry is going to serve you well, right? Because if you want to find the area above 3.49, what could you do? You could find the area to the left of negative 3.49, right? That's fancy. You don't have to do that. You could find the area to the right, sorry, to the left, and then take that -1. Man, somebody stop me. 1 minus that to find the area to the right. There, no one can stop me. All right. So, good. So that's how we're going to use this table. And just as a side note, because it is terminology, yeah, nobody stop me. So these here we call the table entries. Okay, so when I'm talking about table entries, those are going to be the areas to the left of the respective Z. Okay. This is a really old school way of doing it, right? We have, computers, we have phones, we have calculators that can just find these probabilities. So, but you can imagine someone had to go through and integrate this. That's why someone was like, oh no, I'm not doing that again. I'm just going to do all of them once, write them all down, make a table of it, and then we can just use that. And everyone's like, yeah, good idea. Okay, great. So who's going to do that? No one volunteered. No, obviously they did. And so that's what they've done. We don't have to do that anymore. Okay. So we're going to just use this table, and I want you to use this table for questions, especially for assignment questions and test questions, just because sometimes things will be hard-coded and it's using the table. Even though it's pretty old school, we don't really need to use tables anymore. But in a test situation, right, it's definitely easier to just use the table, right, once you're comfortable with it. Okay. There's nothing wrong with using the table. It's just pretty old school. but it's how we teach it. Okay? And so I want to show you how to do it in R. Of course, R can do this calculation for us too. But first, I think we were supposed to find, we had a Z. Oh yeah, we had that very unsatisfying Z. Negative 1.58, it's somewhere between 0.025 and 0.16. Hey, fair enough. Okay, we want to whittle that down a little bit. So first thing I'm going to do is I'm going to have to round this Z to 2 decimal places, right? Negative 1.58. Wow. Negative 1.58. So I'm going to go to the Z table, making sure that I'm on the negative side, right? Because otherwise that'll really mess things up. But you'll develop a pretty good internal kind of check-in point, right? Because you know that the area to the left of a negative Z score has to be less than 0.5, right? Because it's not until you cross that mean that you're up above 0.5. And same thing, if you have a positive Z, then you know that the area to the left has to be more than 0.5, right? So we have these internal check-in points already. We just need to get used to using them. Okay, let's see if I can grab all of this here. Maybe not all of it. How about this? Because I'm assuming you have it. So then I can just zoom in here. So we had negative, 1.58. So I'm going to find negative 1.5 here. It's because I'm all zoomed in here. Hey. Something in between there. I'll do all of them just because, right? And that's what I like about this table is it has the shaded regions. So it does make it a little bit easier to follow across, right? So many times I see people kind of skipping around here. And then I just need to find the second decimal place, which was 8, making sure you round properly, right? And so now what I find is that this area is 0.0571, right? If we think about, so here's the instructions in case you got lost. But the area to the left of Z equal to negative 1.58 is 0.0571. Okay, so we can say that the probability of an observation being less than 3.4, right, from the mean of 5.3 and a standard deviation of 1.2 is 0.0571. Notice that that is between 0.025 and 0.16. Right, so if we go back to here, paste. Notice that. So we cut these so it'll be slightly off, but not enough to care about. Right? This area, this probability is 0.0571, which, so that's true. 0.0571 is between 0.025 and 0.16. So great, we did it. Right, but it's a little bit more precise and it's just easier to deal with those probabilities instead of ranges for the probabilities. Okay. So in R, we can use what's called the p-norm command. So it just does it for us. And I just recently, I saw p-norm of just the z-score. And so we can do this in R. So if we use the p-norm command, which is just built into base R, it takes the x, it takes mu, and it takes sigma. I haven't tried it yet, but I guess, or if you have the z-score, I guess you could just use the p-norm of whatever the z is. So if you have the p-norm of negative 1.58, then it should give you the same thing here. This one's going to be a little bit more precise, right? Notice how 0.05667275 is slightly different from 0.0571. Why is that? Because we had to round our z-score, right? Whereas R doesn't have to do any rounding. It can just go for the exact value, right? And so this answer is slightly different because we had to round our z-score to 2 decimal places. Oh. Yeah, so in terms of comparing these values, I'm not concerned about those differences, but I am concerned about the difference between a range of 0.025 and 0.16 versus the more precise value of 0.0571, right? But the difference here is minimal. Doesn't matter. But that's why it's different, is because it's using more precise values. So notice if you use the p-norm of z, you would have to calculate that z-score, right? Here, you're just giving it the components of the z-score, and then it calculates the z-score for you. There are situations where you might just have z-scores. You might only have standardized values. So then you could just go in and use the p-norm of z instead. Okay, good. I'd be curious to try p-norm of negative 1.58, but it should end up being 0.0571 exactly, right? Okay, but like I said, I haven't tried this one. I saw it and I thought, oh, cool. Moved on. Okay, good. One thing that people always have a hard time with, and I've mentioned it already because it is such a common problem that I am asked about. If we find z-scores beyond negative 3.49 or positive 3.49, those are kind of beyond the table range, right? Of course, if you're working in R, it can handle it. It can find those probabilities. But if we're working with the table, then what we can say is the area in the tail is approximately 0, right? Because from the Z table, we saw that already, right? We know that Z keeps going to positive infinity and negative infinity. Oops. Z is centered on 0, but they stopped reporting values. Well, you have to keep your table kind of condensed, right? So what they decided was, okay, we're going to stop reporting values after negative 3.49 and positive 3.49. Z-scores happen beyond those points, but what we know is that, okay, well, this area, we know from the table is 0.0002. Okay. We also know that this area, we saw it just before 0.9998. Or usually the probability, right? If we're talking about the probability of having a Z-score that's larger than 3.49 is 0.0002, very, very small. So we don't really care about, you can say it's, right, technically, we would say that the area in the tail is less than 0.0002, right? But approximately 0 is fine as well. Okay, so what we can say is that this is or approximately 0. Okay. It's really important that we don't say the probability is 0. Why is that? Because we know as a fact, this curve, it never closes on the axes, right? And so we can never say that the probability is 0 because there's always a probability of something happening, okay? And so I'm gonna highlight that because I will take marks off if you tell me that a probability is 0. I'll even write that in red. Okay. I will take marks off if you say the probability is 0. Uh-oh. The probability of winning the lottery is not 0. It's 0 if you don't buy anything. That's fine. But we assume that you're playing. Yeah, so yeah, so that area gets very, very, very small, and we don't care how small it is after that point, right? And so, like I said, there is going to be a question, or there's always a question where a Z is way out here in the tail. Let's say you find a Z score of 12. What's the probability of seeing a Z score as extreme or more extreme than 12? Well, approximately 0. Okay, so for example, if you find that Z equals 12, okay, the probability of finding an observation as extreme or more extreme, that's usually how we talk about the area in the tail, because that's what we're going to want to figure out is what's the probability of seeing something as extreme or more extreme. And that's what we use to make decisions. If you have heard of p-values before, that's all it is. It's the probability of seeing something as extreme or more extreme than what you saw. Okay, and so we quantify kind of how extreme something is by that p-value. So, and it is just a probability. So the probability of finding an observation as extreme or more extreme is approximately 0. You could say, or you could say it's less than 0.0002 because that's the last cutoff point that we have, but I get lazy and I say approximately 0. So, or less than 0.0002. Okay, because what we have is we have Z and it's centered on 0, and I found a Z out here of 12, right? This area is definitely less than the area from over here. 3.49 has an area. So all we can say really, if I've moved far enough out into the tail here, is that it's less than 0.0002 or approximately 0. Okay. But they do happen. It can happen. It's just unlikely. Okay, good. So I can never seem to emphasize that enough, because I'll always get answers or questions about it. What am I supposed to do? Did I do something wrong? I've calculated this Z score so many times over. I think I'm doing it right. You are. What's another thing that we could do? We could have probabilities, and then so we could kind of dictate the probabilities that we want, and then we could work backwards to find the cutoff. Okay. And it looks like I'm not going to have time to work through the example, but I'll save that for tomorrow. For a little tidbit. I think it'll be perfect to wrap up this section tomorrow. So using the Z table, we're going to be able to find probabilities. And if we have a probability that we want, right, we can find the cutoff by working backwards. I call it working backwards because usually we start and we say, okay, if I have a Z of 3.49, then I can find probabilities associated with that. So now I'm working backwards in the sense that I'm dictating the probability that I need. What cutoff makes that happen? Okay. And so I have an example. So if you want to, you could go through and try the example on your own, and then we'll work through it tomorrow. But what it's going to look like is you're still going to have some normal distribution, and maybe you force this area. Maybe you force this area to be 0.1, 10%, the lowest 10%. Then what would you want to find? You'd want to find what value makes that happen. What would you do? Well, you could find the area to the left closest to 0.1, and then you can map it back to a Z score, and then you can unravel the Z score to get to an X. But I'll show you. You can try it, and I'll show you where that. We're going to use this example 6. So the cereal manufacturer, right? We've got some mean, we've got a standard deviation, and then we want to find probabilities. And I've shown you the R code that you can use to solve these problems as well. So you have the answers, sort of. Okay, I know I'm out of time. All right, good. So try that, and then we'll sit down and we'll do it tomorrow morning. If you have any questions, let me know. Otherwise, see you tomorrow. Or not, if you're taking an extra long weekend. That's fine too. And I'll stop this recording here.